It's still loading, but it's showing.
Yeah, so you usually use Zoom. So Google Meet, whenever I use, I mean, if I have to give through Google Meet, I face this kind of issue. So, mm,
One thing we can do, if you can mail it to us, we can present it from here, and then you can control it from there. You just say next slide and all, and we can
okay,
accordingly.
okay, let them do that also. That is better.
You may kindly send the presentation to me.
Okay, so yeah, give me 2 minutes. I will send that. Mm,
Oh, is presenting from camera. Yeah, I'll use that. I'll use that. Actually, this can be fixed from here, so it's much better that way.
From bottom, you look an awkward figure.
okay, I have sent you. So if you receive, you can open. Let me know. Mm, in the meantime, let me try again.
Joel, can you hear me?
Yeah.
Uh,
Did you receive my file?
yes, I have received your file, and I'm arranging to present it from here.
Mm-hmm.
Can you hear me, Joel? Joel?
Yeah, yes, sir. Yes, sir.
Please see that I have sent Dr. Pati's presentation to iCurryCode. You present it from there. It is in PDF format, but you can place it there.
Yeah, sure.
Please share the screen from your end and show it accordingly.
Yeah, okay.
Dr. Pati, your screen is still shared. You can stop sharing now.
Yeah. Yeah.
Yeah. Did you get Joel?
Yeah, got it, sir.
So you present it and let me know.
Yeah, just
And you also let on the live streams. Yes, it's coming. Yes, it's coming. Get to full screen. Can you see it, Dr. Pati? Is that all right?
yeah, I can see you. Yeah.
Okay, so we can proceed.
Yeah. Yes.
Okay, so I'll just begin the program. I'll give a very short introduction and I'll hand it over to you. Right?
Yeah.
Okay, Joel, are we ready with the live stream?
So make it full screen. I think it is still not full screen.
It's coming. It will be arranged to full screen.
Yeah, live streams are ready.
Yes, you make it full screen. The presentation, you make it full screen. In view, probably you'll get the option to go full screen.
Yeah, go to view and then make full screen. Yes. Yeah, in top. Yeah. Okay.
Okay, is that all? Okay. Okay, welcome viewers, and a very good afternoon to all of you. I am the project coordinator and curator of the Regional Science Center and Planetarium Calicut. You all know that even though our center right now is not allowed to go for public programs with physical presence of the people here, but it is our continual effort to engage with all with the message of science, be it the pandemic, be it related to the pandemic or otherwise. And we felt that during this pandemic period, while definitely we should talk about the pandemic and its associated issues, at the same time, we also tried to look towards other happenings in science because they are also important, and we were trying to connect to people with the messages of science from different streams and different cutting edge ideas. One of them is here today, and we are very lucky and fortunate to have a very prominent scientist among us, Dr. Arun Kumar Pati from one of the most esteemed institutions in India. It is the Harishchandra Research Institute. Dr. Pati is a professor there. And I'll just give a very small introduction to Dr. Pati, though probably those who are into this field of quantum computing, they know him quite well. He's an internationally renowned scientist. Professor Arun Kumar Pati is internationally known for his work in area of quantum information theory, quantum computation, general quantum theory, and foundations of quantum theory. Quantum information and computation is a promising field, you all know, and it is a research field where active researches are going on all over the world, and India is no exception. And Professor Pati's work has been represented on the cover page of Nature. He has become he has captured headlines, news headlines quite often. I remember that I first saw news about him probably somewhere in 2006 or 7, and from then onwards, quite frequently, he has fared in many of these newspapers, media, but in the professional circle, he has been a very, very well-known and renowned professor of this particular subject. Now, you all know, those who are students of physics, that quantum mechanics creates some kind of intrigue. And Professor Pati is an expert on explaining all such things. We'll have a chat probably afterwards. But before that, I hand it over to Professor Pati for his today's deliberation, quantum computing and quantum information technology. Thank you so much, sir, for joining us, and it's all yours.
Okay, thank you, Manoj, for a nice introduction. So today I'm going to tell about this exciting field of quantum computing and quantum information technology, and I will try to give a flavor of recent advances over last 20 years or so. So hopefully, this will be motivating for the young generation. So as you see, myself is at HRI Allahabad, and we have here one of the largest group in India in this field. So can you go to next slide? Okay, so what I'm going to do today, I will tell briefly about quantum computing, quantum communication, and quantum cryptography, and what is this field about quantum information technology, and what is the future of this quantum information, and finally I will try to summarize what I have told during this talk. Okay, so next one, please. So all of you know that when you deal with the classical information processing devices, we know that all the time we manipulate a string of bits. Okay, when you think of string of bits, essentially you store your information, in bits, which is the basic unit of information, like 0 or 1. So what is 0 or 1? Essentially it means that you identify two physical state of a classical system, and you say, okay, if it is say on, it is 0, if it is off, it is 1, or anything you can think of, and that will constitute a you can encode a single bit using that physical system, and then you can do various tasks according to your desire, according to your goal, and so on, using classical laws of physics. When I say classical laws of physics, what I mean essentially you use your Newton's law or your Maxwell's equation and so on in describing the physical process. But what happens is you never find, these classical bits in combination of these logical states. That is, if you deal with classical information, you will never find your logical bit which is both 0 and 1. Okay, it is either 0 or 1. But that changes when you go to quantum domain. Okay, so next one, please. Next slide. So when you think of computation, I mean, we have seen tremendous progress over last several decades, starting from early computer era to even desktop to laptop, even to mobile and so on. But essentially, it is a device where you have a string of input, string of bits as the input, and there is a processor which processes information, and then you get the output. So typically, your computer is something essentially input, you process, and then you get some output. Okay, this is the simplest way to imagine a computer. Okay, next one, please. And when you think of a communication, essentially you have two persons, Alice and Bob, or could be sender, could be receiver, and then you have to send information through some channel, and that is your communication channel. It could be face-to-face, it could be internet, could be telephone, or could be email, could be fax, anything you can think of. And then receiver will receive the information, and then he or she will decode the message. And if they want to do back and forth communication, again he or she can encode and send it back to the other person, and so on. So this will constitute a communication cycle. Okay, typically this is what happens when you think of classical communication. Okay, next. So before 80s, people have been thinking about this information science and physics. They were thinking that maybe they are two different, different topics. They are not connected. But it is a great insight due to Rolf Landauer, one of the pioneer of classical, reversible computation, he realized that any computation is essentially a physical phenomenon happening in a physical system. So once you realize that physics and information, they are not really disparate, not really different subjects, they are intimately connected. And that led to a profound insight, what is captured here. Essentially, he said that information is physical. And that leads to this view, so-called physics of computation. And this has so much impact on the, in the late 90s, that people like Charles Bennett and many others tried to think of reversible logic gate, reversible computation, and ultimately that led to imagine or led to think, that opened the door towards also quantum computation. So this played a very important role, and still continuing to play a major role, in trying to understand quantum information and its connection to physical system. And all of you will agree that physics is deeply involved in fundamental work, which ultimately leads to various technological developments. You can cite many examples, starting from computers to internet, to electronic devices, to communication systems, and recently this emerging technology, what I'm going to tell today about, so-called this quantum information technology. Okay, next. So coming to this quantum computing, you may wonder how this field started. How did this field, or who initiated this field? So essentially, it is due to Richard Feynman's insight, who started to realize that if you have to simulate a complex physical system on a classical computer, that will be very, very inefficient. So then he realized, maybe if you exploit quantum system, maybe it can simulate more efficiently. But he didn't have any clue how to proceed further. So, but this question was very important at the time in 1982. So he raised this question: what can happen if you store information in two distinct states of a quantum object? And this insight was taken forward by a British physicist called David Deuce, who actually laid the whole foundation of quantum computing. So he, in some sense, is the father of quantum computing. So David Deuce, in 1985, he realized that not only you can store information in distinct state of a physical quantum system, but also you have this so-called quantum mechanical superposition principle. And once you have that, what will happen is that not only you can store information in 0 or 1, but also you can store information in 0 and 1. Okay, this is a new possibility that emerges naturally, when you think of quantum systems. And essentially, he realized that quantum computers are devices which you can build using the principles of quantum theory, the ultimate theory of nature. As I said, this idea is originally due to David Deuce, and this came in 1985, and subsequently in 1989 also he wrote another paper. So these two papers in 85 and 89 actually constitute two major developments in quantum computing. I mean, the founding pillar of quantum computing. Okay, next one, please. So here is a citation from Royal Society of London, when he was awarded this Fellow of Royal Society. That citation goes something like this. So David Deuce laid the foundation of quantum theory computation and has subsequently made or participated in many of the most important advances in the field, including the discovery of the first quantum algorithm, the theory of quantum logic gates, in quantum computation and network, the first quantum error correction scheme, and several fundamental quantum universality results. So, as you can see, I mean, his results really span a wide variety of things in quantum computing, starting from the initial proposal of building quantum computer to quantum algorithm, quantum error correction. So many things he actually did. So this is really remarkable what he did. Okay, next. So there is another motivation coming due to Moore's law, which says that number of transistors on a chip doubles every 24 months. And this has been a guiding principle for high-tech industry since it was coined by Intel co-founder Gordon Moore in 1965. A decade ago, you could find that chips were built around 500 nanometer level, and few years back, IBM announced to build chips at 7 nanometer. Maybe it is also trying to reduce even, the scale. So in future, they may even build it at much smaller scale. Next. So this is the figure that you see when you think of this Moore's law. So number of transistors essentially grows like this. And if you extrapolate by 2030, you will see that transistor will need to be about 2 nanometer. That is essentially 4 atomic distance. So which means we know that once you go to the atomic scale, your conventional classical physics will break down, because you cannot apply Newton's law, you cannot apply Maxwell's equation, and so on. So we have to use quantum physics to store and process information. And that is another reason. This is not the only reason, but one of the early motivation was also to see whether you can bring quantum effects by going down to atomic scale. Okay, next. So let me tell you essentially what this quantum bit is. What do you mean by a quantum bit? So as I said, a classical bit you can find in 0 or 1, but because of this quantum superposition, you will find that a quantum object can remain both in 0 and 1. So what it means? It means that think of a single electron. Okay, so electron has a spin. It is spin up or spin down. So if it is spin up, you say it is 0. If it is spin down, you say it is 1. But then we know that an electron can also remain in a linear combination of this alpha up and plus beta down. That is because of this wave particle duality, which you are all familiar in our graduate level course. Quantum object also, they satisfy this strange feature, that is, they can also remain simultaneously in both up and down. Which means if you translate this physical state to logical state, it means that you have a state where your logical state is both 0 and 1. Okay, so this observation is the first demarcation that you see when you go from a classical bit to a quantum bit. Okay, and you can think of also photon polarization, you can think of atomic level, you can think of ionic level, and so on. So any two distinct quantum state once you identify, you can say, okay, one state will be 0, other state will be 1. But then at the same time, you can also have a situation where you can design your quantum state to be both in 0 and 1. And that inherent parallelism is responsible for the new type of computation that will, gave rise to whole field of quantum computing essentially. Okay, next one. So here is a pictorial way of looking at that, what I said. So you identify two state up and down, but then by superposition principle, you could have a situation where you can have alpha up plus beta down. But if you want to do a measurement on a quantum system, that is, if you want to read the result of your computation, you do a measurement, and that will essentially end up again up and down. So you can again end up only with 0 or 1. Okay. So even though your quantum bit can exist both in 0 and 1, but to be able to extract some possible outcome, which could be a result of your computation, essentially you do a measurement, and that will end up either 0 or 1. So if you're dealing with many quantum state or quantum bit, again you will end up with a string of bits, string of outcomes like 0, like up, down, down, up, and so on. So that means essentially you have to convert to classical information. Next one. So if you think of a situation where you handle with 2 quantum bit, then you see what happens. So we know that 2 classical bit can remain in one of these 4 logical states like 0, 0, 0, 1, 1, 0, 1, 1. But if you think of a quantum bit, they can also remain simultaneously in all these 4 logical states because of this so-called quantum superposition. Next. So if you now imagine n quantum bit, you see what happens. So compared to classical scenario where n bit can be in one of those 2 to the power n possible logical state, this quantum computer, which is consisting of n quantum bit, they will be able to have a logical state which will be a superposition of all those exponential number of logical states. So you see the number of states that a quantum computer is able to access is exponentially large, in number of qubits. So that is the power, which the people realize in early days of this, and that's where this exciting thing, excitement happened, and then this whole field emerged. So as you can see, if you think of a situation where you deal with n, say 300 number of quantum bit, that goes something like 10 to the power 90, which is more than the number of atoms in the known universe. So you see how large, how vast this exponential number of logical states is. And quantum computer essentially take the advantage of this exponential number of logical states, which often we call as massive parallelism, because you are able to access parallelly both the logical state, okay? Or in case of n qubit, you are able to access parallelly all this exponential number of states. That is why you say it is massive parallelism, which is offered by, this quantum theory. Okay, next. So you can ask, what can you do with quantum computer? Okay, so this is the one of the most important question that people have been wondering about. So technological revolution from quantum computer may allow to solve problems that are currently too complex for classical supercomputer. So in early days, there have been few algorithms like source algorithm, which you can use for factorization. There was this Grover's algorithm, which you can do for database search, and there was this Joja algorithm that was designed to decide nature of this function, which was essentially to highlight, how quantum computer can be more efficient, more powerful compared to classical computer. Next one. So building a quantum computer is the race of the 21st century, which is a difficult and ambitious challenge. And it has potential to revolutionize future computers that can do impossible calculation with a plethora of useful applications in healthcare, even defense sector, finance, chemistry, and even material design or development, software debugging, aerospace, and even transport. And the speed and power of quantum computer lie in the fact that the quantum system can remain in multiple quantum states that only occurs at the quantum level. And we need to bring quantum computing to commercial reality, and we need a extraordinary team to put their effort. And that is why you see a lot, 3 to 5 years, a lot of private companies, a lot of academic institute, a lot of government are actually investing a lot of money in this area to build quantum computer. Okay, next one. So already we see a global race for building quantum computer. So for example, in 2016, IBM initiated to build commercially available universal quantum computing system with 5 qubit. In May 2017, IBM Q was announced, a prototype commercial processor with 17 qubit, and that has significant improvement compared to what it was. So it was most powerful computer at that time. And last year, in September 2020, IBM announced a 65 qubit quantum computing processor, and by 2021, they plan to have 127 number of qubit, and by 2022, they want to build about 433 number of qubit, and in next 10 years, in next 2 years, they want to go about building 1121 number of qubits. Next one. So once they build this, they want to have, so that everyone can use. For example, you can allow developers, you can allow programmers and researchers to implement quantum algorithms and other information processing protocols. And already we see that there are more than 30 companies have already started investing in quantum computing and quantum information technology. And you might have seen in news item last year. In fact, also last year, that Google achieved so-called quantum supremacy. And what is that supremacy? Essentially, it is a terminology that you reserve for this. That is, if your quantum computer can solve a problem that no classical computer can solve in any feasible amount of time, irrespective of the usefulness of the problem, that is, whether your task is useful for societal benefit or something else, don't care. But at least if you can claim that yes, your quantum computing processor can actually solve much faster compared to all the existing supercomputer, then you will say, okay, you have achieved quantum supremacy. And also there is something called quantum advantage, which essentially is the following, that if you can demonstrate that the quantum computer can solve a problem faster than classical computer, then you will say that it has achieved some advantage. Okay. Next one. So they said in 2013, Google claimed this quantum supremacy with these processors, and that had about 54 number of qubits. The task they implemented was something essentially to check the random number generation, which the best supercomputer will take about 10,000 years, but with this Sycamore processor, they could do only in 200 seconds. So you see the imaging power of this quantum processor, this 54 number of qubit. Last year, in 2020 December, this Chinese team they tried to design another processor which is 10 billion times faster than Google's processor. So it took about 200 seconds, whereas world's fastest supercomputer might take approximately 2.5 billion years to carry out the same task, which essentially brings out a clear example of quantum supremacy. Next one. So when you think of quantum computing, quantum information, often you will see, or you will read some article where they talk about quantum entanglement. So what is that? So entanglement essentially is a strange kind of feature that happens whenever you deal with two or more number of particles. Okay. So essentially what happens is, if there are two particles which are in an entangled state, then it is not possible for you to associate a definite state for an individual system. That means individual quantum states are not independent. They are linked in a strongest possible way, even if they are far apart. That means if you prepare two entangled particles in your lab, and you send one particle to, say, Delhi, other particle to, say, to New York, as long as you can maintain their entanglement, they will behave as if a single entity. Okay, so this is the miracle of quantum entanglement, and this the weirdest feature that you see in quantum world, and that allows you to do many imaging tasks which are otherwise impossible. And I will try to highlight some of the tasks which you will see in next couple of slides. Okay, next. So quantum entanglement essentially involves entwining two or more particles without physical contact, and this provides an invisible kind of link between two or more particles, which you can use for quantum communication. Next. So you may be surprised to know that entanglement is one of the hot topic now. I mean, now means over the last 25 years or so, but it was already discovered way back in 1935 by Schrodinger, and later on, not later on, in the same year actually, by Einstein and Podolsky-Rosen, in trying to argue that quantum theory may be not a complete theory, because if you read the history of quantum mechanics, we know that Einstein was not really very happy the way quantum theory was being developed, because unlike classical world, quantum theory brought some kind of indeterminacy, some kind of probabilistic element, which was very, very uncomfortable for Einstein. So he thought that maybe quantum theory is not a complete theory, there is something beyond quantum theory. So he used this entangled state to argue against quantum theory. So he along with his colleagues, they found that entangled state displays strong correlation between space-like separated particles, and this spooky action, which they called, and which according to them was very strange, but now we can exploit for quantum computation and quantum communication. Next one. Okay, so thinking about quantum information and quantum bit, there is something even remarkable about these quantum bits, because they are in some sense private. Because once you store information in quantum bit, nobody else in the world can know what information is actually stored in this quantum bit. So in that sense, the information stored in quantum bit, they're private. Okay, so there are some results that was proved in 1982, like so-called no-cloning theorem, which says that quantum information cannot be copied, which essentially means that given a quantum bit, if you have stored some information in that quantum bit, only you can make a copy. Nobody else in the world, nobody else in the whole universe can make a copy of this information. And later on in 2000, we also discovered something called no-deleting theorem, that which says that quantum information cannot be deleted. And in 1999, there is something called no flipping, that you cannot flip an unknown quantum bit. Like classical information, you can make a not get, like 0 can flip to 1, 1 can flip to 0, but quantum bit you cannot flip. Next one. And also in 2007, we discovered something called no-hiding theorem, which was trying to explain the issue of information loss. Okay, so typically when we encounter some physical system, and if we see that information is lost, we may ask the question, what happens to that information? Is it really lost, or it has gone to somewhere else, and what is actually going on? So you can show that information is not actually lost, but it moved to some other system, and that essentially proves the conservation of quantum information. And that was also tested using NMR's quantum computing setup in IISc in 2011. And very recently, we tried to prove something called no masking theorem, which essentially tells that if you want to store information not on the physical body, but only in the quantum correlation, so-called spooky correlation, so that locally this person, Alice and Bob, they will not be able to see the information. That means as if you put a mask on this local entity, so that you don't see their face. Okay, you don't see the information, but it is globally it is there. Is it possible? And we found that that is not possible all the time. Sometimes you can do, but not all the time. And these results have deep implication in quantum information and quantum communication. Okay, next one. So if you ask the question, what is going on in quantum information? What is the big goal, a big picture? Essentially, here in 2 lines, I said what typically we explore in this area. So one of the main goal in quantum information science is how well we can store, process, and transfer information contained in a quantum state using principles of quantum mechanics. Okay, that is one of the big goal. And in this exploration, essentially we use these features like superposition, entanglement, quantum non-locality, and we exploit these features for practical applications and for doing imaging tasks which are impossible otherwise. Otherwise, it means in classical world you cannot do those tasks, because in classical world you don't see this kind of features essentially. Okay, next one. So here is a scenario where you think of a quantum communication channel. So quantum communication essentially means you send quantum information using rules of quantum theory and using some quantum and classical resource. Okay. So Here you see two person, Alice and Bob, and Alice and Bob, they have to, before starting the protocol, they have to establish some kind of quantum channel, which means they have to distribute some entangled state beforehand. And what they can do locally within their lab is anything that is allowed within quantum mechanics. Okay. Don't worry about what I said here, unitary measurement. If you don't know, I mean, don't worry, because for this you need little more understanding about quantum mechanics, but don't worry too much about this. Essentially, Alice will do something to her particle, which is allowed, which is physically possible, which means that should be that particular operation that Alice is going to do should be allowed by quantum theory. That's all. Okay, that's all you need. And then depending what she does, she will communicate over classical channel. As I told in the beginning, classical channel could be internet, could be telephone, could be fax message, anything you can think of. And depending on that message, Bob will also do something, and at the end, they will achieve the task of doing quantum communication. Okay, next one. So coming to quantum communication, you see many, you will see many developments, but I am not going to tell all the details. So I have highlighted few things here, like quantum teleportation, super dense coding, remote state preparation, quantum secret sharing, quantum cryptography, quantum internet, and these are the few things that that will play a very major role in next in next couple of years, because already we see like Chinese group, they have implemented quantum teleportation over long distance and so on. So I think these protocols will play a major role in future quantum communication. Next one. Okay, so thinking about teleportation, if you have seen this sci-fi movie, you might have seen this Fly or maybe some other Star Trek or something else. So essentially, teleportation is a process. You want to build a device, okay, where you want to send a person. That means the person will enter the device, and he or she will, press a button, and then he will disappear from this location, and they will reappear at another location. And the distance is immaterial. It could be another planet, it could be another extraterrestrial object or something else. And essentially, that is the process of teleportation. So if you look at the dictionary meaning of teleportation, it is essentially destroying an object at one location and recreating the same object at a distant location. That is the meaning of teleportation. So if you ask the question, can you teleport a quantum object? So before 1993, it was thought that it is completely impossible. Why it is impossible? Because to teleport, what do you need? For example, if I want to teleport this object, okay, essentially what this machine had to do is this machine had to read all the information content in this person, for example, and then send that information to the other end. And at the other end, this would have some raw material, and depending on this information, that the device at the other end should be able to recreate, from this this whole object which was to be teleported. Okay, but if you are giving a single quantum object to a person who would like to teleport that, we know that he or she cannot read the full information, because by no cloning theorem, he is not allowed to know the information. Okay, he cannot make any. He cannot make. He cannot have any knowledge about the information content of this quantum state if that is to be teleported. So it was thought that it is completely impossible to do teleportation. But this Charles Bennett and many other people involved in that paper, so they found a way to teleport this quantum system. So next one. So here is the scheme. So you have Alice, you have Bob, and Alice want to teleport a quantum state to Bob. And what she will do is that before starting the protocol, they have this so-called this entangled channel. They have already shared this entanglement. And then Alice will do something on this input and this half of the entangled particle, and depending on that something, he will send this only 2 classical bit, and Bob will do something to this particle, and at the end, this particle will get transformed to the input that Alice wanted to teleport. So you see, in the whole process, Alice is not able to know what is there in the state psi. Neither Bob also know what is the information contained in the state psi. So unlike classical teleportation, this quantum teleportation is an beautiful and amazing application of this quantum entanglement, because you see this entangled channel actually somehow able to transfer all the information without even knowing what is there. Okay, and this whole process is completely secure, because if you try to tap this channel, you will not know anything. If you try to tap this channel, you will not know anything about the state psi. But together, if you take this quantum channel and classical channel, then you will be able to recreate the states. That is the whole idea of quantum teleportation. Okay, next one. So this is the first theoretical idea came in 1993, and immediately in 1997, this Vienna group, they did the experiment, and they could teleport the single photon over few meters across the table. Okay, that's the first prototype experiment. And here you see the 6 scientists who discovered this quantum teleportation. Next one. And subsequently, people try to teleport information from light to matter, and then they try to teleport between different objects and so on. And they try to see if you can do over long distance, and it cannot be eavesdropped, and during transmission of the quantum information, it can remain unconditionally secure. So all these things people have achieved. Next. So this is the Denmark group with the teleportation of information from photon to atom. Next one. And later on in 2003, this Geneva group, they teleported a single photon over some 55 meters, and then also they did over 2 kilometer distance. And then this Chinese group, they also did over something like 16 kilometer. And Japanese group, they teleported a single photon over 100 kilometer in 2015. Next one. And 2 years back, this Chinese group, they reported the ground breaking experiment where they teleported single photon from ground observatory to low Earth orbit satellite through an uplink channel, which is covering a distance like 1400 kilometers. This is the record-breaking distance this Chinese group actually implemented quantum teleportation. And not only they did that, they also could demonstrate how good that is, that they could quantify up to 80%, that yes, indeed it is working. Next one. So next, quantum communication. This is not really quantum communication, but this tells you that even to send classical information, quantum theory can actually help. Why? Because we know that if you want to send a single qubit, you can get only 1 bit. As I said in the beginning, even though quantum bit can exist both in 0 and 1, but once you do a measurement, you get only 2 possible outcomes, and that will lead only to a single bit, because log base 2 times number of distinct outcomes, essentially log base 2 times 2 is just 1. Okay, so essentially you will get only 1 bit. But what happens remarkably, that was discovered by Bennett and Weisner in 1992, was that if Alice and Bob, they share entanglement, which is a kind of quantum channel, then by sending a single qubit, you can actually send 2 classical bits. That is why the name comes super dense coding. So this is another remarkable application of quantum entanglement, that not only it helps to do quantum teleportation, but also it can enhance your communication capacity, classical communication capacity. Okay. Next one. So here is a pictorial way what I said. So you have Alice and Bob. They have this entanglement shared beforehand. Then Alice wants to send 2 classical bits. Then she will encode this by doing something on this particle and send that particle to Bob. And Bob will do some kind of operation, and he can get 2 classical bits. So as I said, if they don't have this entanglement, just sending a single qubit, Bob will get only 1 classical bit. So that is the enhancement of ability to send classical information using quantum entanglement. Next one. So unlike quantum teleportation, in 2000, what I propose is something called remote state preparation, where Alice wants to prepare a quantum state at a distant location without physically sending it. So it is like this. Imagine that you and you are in your home, and there is this lockdown, and you want to help your friend to prepare a particular dish, particular item, in his or in her kitchen, So what can you do? Either you can prepare your food and pack it and send it by some courier, and you reach your friend's place, and friend can enjoy your food, Or alternately, what you can do is you can tell the whole preparation procedure, whole recipe over telephone, and then Bob can prepare the desired dish, But can this be done without these 2 means? That is, without telling the whole recipe, without sending the recipe, prepared recipe by courier, can you still do this? The answer is yes. And this is not recipe, but this is not preparing a dish, but preparing a quantum state, which I call remote state preparation. So Alice wants to prepare a quantum state that she knows, but Bob doesn't know, and that she can do by again using one entanglement pair and doing something and just sending 1 single bit of classical information. So this idea was proposed in 2000 and also experimentally tested by many groups later on. Next one. So here is the idea what I said. Alice and Bob, they're at different places, and Alice want to help her friend, so that he can get this quantum state psi. So she is trying to prepare this quantum state psi, which is in her mind, and that she can do by using this entanglement and using just 1 classical bit. Next one. There is also this remarkable direction of secret sharing, because here what you want to do is you have 2 persons, Alice and Bob, and you want to have a joint account. Neither of them should have access to the account, but together they can withdraw some money. And to do that, they require a password. So think of the scenario. So Alice had this message, and this is the key, So neither Alice nor Bob have the key, but if Alice does this XOR operation, that is addition modulo 2, and sends message to Bob, Bob can get the message, So neither Alice nor Bob has any information, but together they can have the complete information. So this kind of idea people are trying to generalize, actually have generalized to quantum domain, and there are many quantum secret sharing protocol where single person cannot have any knowledge about the information, but 2 or more number of parties can have knowledge about the information. So next one. So there is another area that is quite promising is cryptography. So essentially, this is art of encrypting and decrypting message in codes in order to ensure their confidentiality and authenticity. And as we know, the fundamental task of cryptography is to allow 2 users to have a secure communication, which is unintelligible to any third party. Next one. A typical scenario is your one-time paired. You have a plain text, you encrypt and send the ciphertext, and then the receiver can decrypt and get the plain text. And very early example of this kind of scenario is your one-time pair, so-called your cipher, which you can use to do this kind of encoding and decoding. Next one. So in quantum cryptography was proposed by Bennett and Prasad in 1984. So essentially, Alice and Bob, they want to establish a secret key. So they will have, Alice will send some quantum thread through quantum channel, and then Bob will do some random measurement, and then he will announce this encoding bits, and and then at the end they will discard some outcome, and they will end up with some secret key. Okay, next one. So quantum internet is another proposal where a lot of promise is there, and essentially what you do is you want to encode information, process and store in quantum node, and then nodes are connected by quantum channels that can transport qubit from site to site, and then you can distribute also this quantum bit over entire network, and at the end of the day you could establish a quantum internet. That means you could download quantum bit, you can download entanglement, and you can use it for quantum computation, quantum communication, and you can also, you can give it back to quantum nodes also. Okay, this was the idea proposed by Kimball in 2008. Next one. So this is a pictorial way of showing what I just said. So you have some quantum node, and you have quantum node, you want to connect all the nodes. You can do teleportation between these nodes, or you can do remote state progression, and then you can establish long distance quantum communication network, or you can also establish some link between quantum computer or distant node also. Okay, next one. So quantum technology is actually quite vast. I just try to highlight a few things, but this is a technology that has far-reaching innovation based on fundamental laws of nature. So quantum information technology will make devices smaller, faster, and much more powerful than the present-day electronic devices. And as I told few things during my presentation, you can imagine starting from quantum computer to quantum software, quantum information system, quantum communication scheme, like teleportation or this remote state preparation or quantum internet. Not only that, also people are trying to build atomic clock, which will be having high precision, and also trying to build quantum algorithm for tackling hard problems, and for Earth to space quantum distribution, and it will change nearly every aspect of future life. Next one. So quantum computing and quantum information is not just a field where we need, experts or people or scientists only from one domain. We need a multidisciplinary approach. We need people from quantum theory, we need from computer science, we need from engineering, from information theory, from communication, cryptography, from many other branches we need actually. So this is truly an interdisciplinary science, and that is the one of the reasons why many of the companies are joining hands with academia, joining hands with universities, and trying to build up teamwork to achieve their goal. Okay, this is the really an area where everyone can put their effort and achieve something. Okay, next one. Next slide. Okay, so I'm on time. So here is a summary of what I said. So quantum theory, as I told in the beginning, allows you to do or allows you to store information in a new way, and also helps you to process information in a completely different way, which is not there in classical domain. And also quantum information is fundamentally different than classical information, and it exploits principles of superposition and quantum entanglement. And quantum computer can perform certain computational tasks much more faster than the classical counterpart, and that is the reason why there is a global race to build quantum computer. And also I try to convey you that quantum bit cannot be copied, cannot be deleted, cannot be flipped, and cannot be masked, which means once you store information in quantum bit, they are secure at a more fundamental level. It is not that you have to, you have to put an extra effort in making them secure. Of course, there are other issues, but they're like issues like decoherence and things like that. But and a correction, but uh, but these results provide you an extra layer of security, to quantum information that is stored in quantum bit. Okay, next one. And quantum information allows a new way of communication, which I highlighted. And these operations or these protocols are not possible in classical world. And I try to tell you about teleportation, superdense coding, remote state preparation, secret sharing, quantum cryptography, quantum internet, and there are a few more things which I have not included. But if you're interested, you can look at other protocols also. And quantum communication can allow a completely secure way of transferring information. And quantum teleportation is an important protocol that will want to make communication over long distance possible. And in all this, you will see that entanglement plays a very crucial role because that provides this invisible wiring between distant nodes in quantum communication. And one of the biggest challenge is to produce entanglement over long distance. Not only produce, but also you have to maintain, so that you can achieve your goal. And the next revolution will be quantum computing, quantum communication, and quantum information technology. There is no doubt about that. So, next one. I think this is my last slide. So, today's basic science is tomorrow's technology. So, you see, now industry, private companies and everyone is interested in building quantum computer, but the idea came to David Deutsch, who was pursuing pure basic science, because he was a theoretical physicist, he was interested in foundations of quantum theory and so on. So he is the person who laid the foundation of quantum computing. So this is a glaring example of the statement that what you do today in basic science is going to change future technology. Okay, so stay motivated, and if you're interested, there are many lecture notes, many online articles, and many also very good textbooks you can also refer to and you can read. Okay, thank you.
Thank you, Dr. Pati. Joel, you can please switch up the presentation. I invite all to ask their questions if they have any questions. Here we already have a few. The first one that we got is from Dr. Pierre Vedder, who asks an interesting question, Dr. Pati. He asks that in conventional computers, you have input-output devices like keypad, video monitors, etc. What kind of I/O devices would be required for the quantum computer?
Mm-hmm. Yeah, so we are in a situation, or we are in a era where we still don't know what physical system we are going to really make a scalable quantum computer. So that is still not clear. So thinking about keypad and monitor and things like that is far-fetched. I still don't know. So I mean, it's too early to say something really. What kind of system will make out like what you see in classical laptop or classical computer. So, and only future will tell. Yeah.
Okay. We have another question from Mr. Jant Ganguly, who asks that how should we visualize the entanglement? What it is really? Is it something like superposition of electromagnetic waves?
I mean, to some extent, yes, superposition does play an important role, because what happens is when you go to two or more number of particles, essentially it is the superposition of these possible combinations of different states that leads to quantum entanglement. So the answer is yes. Superposition. So think of like this. Okay, think of uh, two spin-off particle. Okay, so you have two electrons. So this could be up, up. Both could be up, up, or both could be down, down, or this could be up, this could be down, or this could be down, this could be up. Okay, but now you see we have also this superposition principle. That means suppose this electron is up, up, and down, down. But then I can also have a scenario where I will have a linear combination of this up, up, and down, down. That means alpha up, up plus beta down, down. So this state is actually an entangled state. Okay, so once you create this state in your lab by some suitable physical interaction or maybe some mechanism, then this state is actually an entangled state. And then once you create it, and you take one electron to your lab and and send another electron to my lab, even if you are in Calicut and I'm in Allahabad, they will remain in entangled state. So that is the miracle of this quantum correlation.
Regarding this, if I may permitted to extend this question a little bit, in one place you told that when the entanglement is broken, you go back to the classical system once again, and you lose the combination and have the definite states once more. Does it mean any loss of information in the process? And is there any further?
Yeah, certainly. Once you do a measurement, you lose this quantum bit. So think of a single quantum bit. You don't have to go to two or more number of quantum bits. So think of a single quantum bit, which was like say alpha 0 plus beta 1 or alpha up plus beta down. Once I do a measurement, I get either up or down. So I lose the initial quantum state. So this is the so that is the reason when you do a quantum computation, you try to maintain your superposition till the time you reach your your target state. Okay, the state that you like to get the final answer, you have to reach the state, and till that time you don't do any measurement. Once you do a measurement, you lose all the benefits that you have obtained. So this is the kind of thing one have to be very careful in trying to implement quantum algorithm. Yes.
So in such cases, is there a concept of any permanent storage?
Permanent storage, I mean, as long as you can keep your quantum bit isolated, without being, without allowing them to interact with the external world, you can maintain. But it is very hard because, quantum states are very, very fragile, I mean, a slight interaction will tend to lose their superposition and you will lose your initial qubit. So designing a permanent thing is at the moment hard, but you never know. Maybe there is a way to shield the collection of quantum bit, and they can still maintain this coherence for a long time. We still don't know that. So these are some of the challenging questions actually. Yeah.
Okay. We have another almost parallel question from Mr. Umesh Kumar Rostage, who is a senior curator in our Nehru Science Center, Mumbai. And he asks if information is lost or hidden and goes to other environment, then how to retrieve it? Is there any way to retrieve it further?
Yeah, good question. So yeah, so what we did in our experiment, actually, we tried to do that actually. I mean, so in our experiment, we had a single qubit, and we did something. Apply something to this quantum bit, and at the end, this information was lost. Okay, but then by our hiding theorem, we tell us that information is not really lost. It must be somewhere. Okay, so we try to look at that where it is. Okay, so we realized that the additional system which is surrounding the single qubit, there are two additional quantum bits. Okay, so we figured out that the information is not here, not in first qubit, but it is simply remaining in one of the additional qubit. So we actually we could reconstruct the original information from third qubit. So there is a way. But if you're, in this case it was a very simple system. Your single system is your system of interest, and the additional system only 2 qubit. So it is much simpler to handle. But if you if you ask the same question in a larger context, that is, if you say this is my single qubit and I have many additional quantum bit, then it may not be that easy to. I mean, infinity is there. The no hiding theorem tells that yes, infinity is actually there, but how to locate, how to reconstruct from this large collection of additional quantum system is very hard. We still don't know. I mean, you see, in principle, it is yes. Answer is yes. It is doable, but in practice, it may be very hard.
The problem may be technically almost improbable.
Yeah. But in simpler scenario, we did verify our idea and it worked perfectly.
It
Yeah.
worked.
Yes.
Okay, then we have another question, another cryptic question from Mr. Ganguly, Mr. Jan Ganguly. He asks that if the quantum bit is not to be, it cannot be tampered, there cannot be any cloning, there cannot be deletion, there cannot be flipping, then what is the requirement of cryptography at all?
No, cryptography is you have to establish a secret key where these two users can have access to that. They should be able to read your information. These theorems sorry, these theorems provide limitation on what you can do and what you cannot do. So, for example, in cryptography, this no cloning theorem actually provides an additional security to the information that is being sent across the channel. That means, suppose LEC is encoding something and sending the quantum state to Bob, then somebody else cannot make a copy of your information. So, no cloning theorem actually provides a security to quantum cryptography. So that provides extra security. Actually. Yeah.
Now, from your presentation, it appears that developing a workable quantum computer takes a long time. Even for IBM, it took somewhere 5 years or even more in another space. Where are the challenges? I mean, what is so difficult that it's very difficult to realize in actually workable form?
Yeah, so the most challenging thing in building a quantum computer, in building a large-scale quantum computer, these two things. One is how to preserve this superposition for a long time. That is called coherence. Okay, and how to fight against error. Okay, because once you have a large number of quantum bits, they will try to interact with each other, and then the thing that you want to encode, there will be some extra error, and that will get amplified and so on. So the error correction and then maintaining the coherence for a long time. These are two greatest challenge, and that is the main obstacle in building or scaling up this quantum computer for large number of qubits. So, and also there is the other challenge. We still don't know. I mean, currently, like IBM, they are exploiting only superconducting qubit, but there are other proposals like ion trap, like photonic quantum computing, like NMR, but we still don't know what kind of physical system will be really you can scale up to say 1,000 number of qubits or 2,000 number of qubits. We still don't know that. So these are the biggest challenges we are still facing. So hopefully, in next 5 to 10 years, something will emerge. So yeah.
So right now, if somebody, it might be very naive, but if somebody holds an aspiration that I would like to be a person who will work with quantum computers and all, what would you suggest for them? Or what to study and in what ways? Is there any particular programming language or particular forms of algorithms that they must?
Yeah. Like IBM, they have developed this QSKit, and then Microsoft has its own software. So there are many already online, and they are freely available also. And there are many institutes. They also teach regular courses in quantum computing, quantum information. Like at HRI, we have regular course, and there are opportunity to do PhD. If somebody wants to do PhD in this area, there are many.
Okay, right now I do not find any other question. I only have a personal. Are you online, Dr. Pati? I have a personal interest that I would like to ask. That I remember that I read some reports about your work where you said that the quantum hiding paradox that is involved with the black holes, that can have a plausible and legitimate explanation. What it is, if you would like to explain it a bit.
Yeah. So don't work too much. Don't really work in black hole, but my interest actually came due to the black hole information loss paradox, when we tried to ask this question that what happens to quantum information when it is getting lost? It is really lost, or it is going somewhere, or what is actually going on? Okay, so with that motivation, we started this question, and we tried to analyze. So we started actually exploring this in 2004, and it took us almost 2 years to figure out the answer. So the no hiding theorem that I mentioned briefly is actually about this. So what we prove is that if there is a physical system, in your disposal or at your disposal, and something happens to that, and information is lost. Okay, this is exactly what happens in black hole. So if you throw a pure state to a black hole, you commit all thermal radiation, and you don't get the pure state. So people say that the information is lost, and there are many proposals to resolve the paradox. Some people say that maybe there is some baby universe where black hole evaporates completely, it goes to some other universe and remains there, or maybe it is hidden in the correlation between the inside black hole and outside radiation, and so on. So our result trying to prove that information, if it is lost, it cannot remain in the correlation. It had to be in some other part of the universe. So then we applied this to black hole information loss, and we ruled out one of the options, that it cannot remain in the correlation. So that was the kind of implication of this no hiding. Yeah.
And one more last topic that I would like you to cast light on is you also have worked on a field where you showed that the uncertainty equation of Schrodinger needs some extension, and it has got some other form as well. What about it, if you may kindly explain it a little bit?
Yeah, so very interesting question that you asked. So when I was a student, in my university, I always wondered, okay, is there anything beyond what we know or what we are taught, in MSc? Because in MSc we all know that we have the Heisenberg uncertainty relation. We learn this Robertson, uncertainty relation. So I was thinking, okay, can there be something else beyond this from which you can derive this, this is a special case of the new relation and so on. So, and that was, I was thinking and trying sometime on and off. And in 2014, myself and one of my collaborators from Italy, we figured out that yes, it is actually possible. So we tried to prove a new relation, okay, for general observables. It could be position momentum, it could be any two observable, and we found that what we have in this new relation is much stronger than what is there in this Heisenberg. So as a result, the Heisenberg relation that we know in textbook actually follows as a special case of that. And then people also did experiment, and they also verified so that yes, it is true. Yeah. So that is the kind of story. Yes.
Okay, so thank you very much for joining us and keeping such a difficult thing simple for explaining to people. Thank you very much, sir. And I hope that in future also will perhaps be some chance to get back to you and get your ideas once again.
Okay, sure. Yeah, thank you.
Thank you so very much. So here we end this program. And bye.
Take care. Yeah.
Thank you so much.
Thank you. Yeah.
I thank all the viewers also for joining this session, and I hope that they were meaningful. And in future, if you have any questions, you can come back to us we can once again contact Dr. Pati, or we continuously work with experts in different fields like this. We will keep on working with such program. Thank you very much for joining. Look forward to seeing you once again in our next programs. Thank you.